Okay, بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. السلام عليكم everyone. So, PD control, geometric PD control, second lecture. Today, inshallah, is really an interesting lecture, at least from my perspective. I don't know how you're gonna be seeing it, but I really enjoyed preparing this lecture. This is really I would say the top of, so the most technical till now, the most technical lecture we're going to be seeing, inshallah. It will have everything piling up just to this moment. And you're going to be dealing today, inshallah, with PD control and SO3. Again, you understand now how fundamental SO3 is for robotics, because again, it's about rigid body orientations. If you have multiple rigid bodies, again, in a fixed base manipulator and a floating base manipulator, just a floating base or just a rigid body floating in air, all of these are models of actual physical systems. This is what you're experiencing now in the project. So learning how to deal with a very simple problem of how to take one orientation and make it into another orientation on SO3 in a geometric way, this is really fundamental. And hopefully today we're going to be answering this question based on a lot of things that we discussed. The first one is Lyapunov's direct method. Just a recap, that given an x dot is equal to f of x dynamical system, and we want to study or analyze the stability of x star as an equilibrium point of the system, we can show it's either stable, asymptotically stable, or globally asymptotically stable if we have these conditions that we discussed several times. The main one is that we need to find a Lyapunov function that's positive definite and has around this equilibrium point, and it's zero. It has a minimum of this equilibrium point. It has a minimum at this equilibrium point, and then it's positive everywhere, at least in a local neighborhood. If you can prove it's globally, it's everywhere, you have this, then you can prove global asymptotic stability. But to do that, you need to be able to find that the time derivative of this function along the trajectories of the system x dot is equal to f of x are always decreasing. If you can show that they're non-increasing, then you can prove stability. If you can show that they are strictly decreasing, then you can prove asymptotic stability. And of course, the last one is usually we'll not be able to have it just because of the topology of the underlying state space. Not just because of that we cannot find the Lyapunov function. Sometimes it's impossible to have it from the topology of the dynamic system. The first, you already saw that from the pendulum, right? So the topology of the pendulum says we have S1, so the configuration manifold is S1. So we have 2 points that are already there that prevent us from having this global asymptotic stability. The same for S2, and in general, even for SO3, we don't have this global asymptotic stability. But we can have this next best thing, which is almost global asymptotic stability, provided that we can prove that the rest of the equilibrium points are unstable, except the one that we're interested in. Lassalle's invariance principle is very powerful, because finding this Lyapunov function that is strictly negative definite is very hard. So usually if we can find this Lyapunov function and we can reach with Lyapunov stability just negative semi-definiteness, then we can extend this analysis based on Lassalle's invariance principle by looking more details on what happens when you have v dot is equal to 0. We built this set that contains of all of the points in the state space or in a smaller domain that has v dot is equal to 0. And then we looked inside of this set R on the biggest invariant set, and then the theorem goes as follows: if M contains only the equilibrium point you're interested in, then we can already show that we have the local asymptotic stability. And again, if you can show that you have this R on all of the state space, then you can conclude global asymptotic stability. Let's recap what we did with the point mass last time. The point mass is just a point in the air living on R3. We have some control inputs, so usually there will be the forces applied to this point. We want this point, so our control objective is to stabilize this point at this desired state, which has a momentum or a velocity of 0 and the desired location of psi d. The PD control law, you're familiar with this: U equal to minus k multiplied by the error, and another gain kd multiplied by the error and the velocity, which is nothing else than the psi dot, and in the end you just get the v. Kp and kt are not just gains, they can be positive definite matrices. So you can have, it's a 3x3 matrix. We can also have the cross diagonal, so off diagonal terms, provided that you can show that this is positive definite. Don't forget this symbol, right? So when we say they have a matrix that is this funny bigger than 0, this means that what? What does that imply? How can we show that this is a positive definite matrix? All of the eigenvalues exactly are all positive. And then you can plug in this U inside of this controller. You can get this closed loop dynamic equation. It's a linear system. You can analyze it as is. But we were interested in extending it or reformulating the same controller as an energy balancing control law by looking at the proportional term is given by the negative of some gradient to some potential function, capital psi. And the derivative term, we derive it from whatever makes the system asymptotically stable by looking at the Lyapunov analysis. And for the PD controller, which is the standard one that you're all familiar with, we can rewrite it into this formulation by having this quadratic function. This is a globally positive definite function. We can show that it's trivial to show that at psi equals psi d we have 0, and at psi, and for any point or any vector that's not psi d, then we show that psi is positive, right? So it's just a quadratic function in n dimensions. And then the closed loop dynamics by plugging in this equation will be given by this equation again. So even for a general psi, so this choice of psi is just particular to so that you can recap this control law just to rederive it. But in general, we can have psi to be any capital psi to be anything, and we can have the UD to be anything. How can we design that? If we look at the Lyapunov analysis by taking the sum of the original energy of the system, in the case of the point mass, it was just half mv squared, half mv transpose v. If you write it in terms of the momentum, it's half 1 over 2 m p transpose p. So if we take this original Hamiltonian, so this original energy, and then we add to it this capital psi, as this potential function that we added from the controller. First, we have this as a global positive definite. You can take the time derivative of that. The time derivative of v, again, you need to look at where does this state live. So we have here x, we said it's psi and p. So psi is a 3 vector and p is a 3 vector. So how do we calculate the v dot? In general, we showed that it's like the Lie derivative in a very general sense. And then we can write this Lie derivative as the pairing between a covector, which we call the differential of psi. The differential of capital psi is a covector, so we pair it with the vector in this way. And again, just remind you with the notation, the d of capital psi is the covector version, while the gradient of the capital psi is the vector version. Because this is R3, so this is just simple, again, column vectors and row vectors. This is a row vector and this is a column vector. In general, we don't have this luxury. Okay, so this is only in R3 that the covector is written like row vector a covector is written as a row vector, while an actual vector is written as a column vector. This is just notation or just a manifestation of the fact that we have the space here is R3, Euclidean space. While the DH, again, we get it from so the P dot, we get it from the dynamics. And again, you can just follow what we did last time, and we already have that these two terms cancel out. They cancel out just because of the fact we chose U to be the gradient of this capital psi. So this gives us a general way how we can just choose psi, and then you're going to get the control law of the proportional term. While the derivative term, we just look at this equation and say, okay, I want this to be negative, to be non-increasing, so I just choose it to be minus kd multiplied by v. I get that the v dot is equal to that. It doesn't include all of the states of the x. It includes only the v, which means we can conclude only it's negative semi-definite. But again, using LaSalle, we can continue and show that it is truly asymptotically stable. And because of the fact that psi is actually everywhere quadratic, so it's quadratic everywhere and it's globally asymptotically stable, then we have, so it's globally positive definite, sorry. Then we have that the equilibrium point is globally asymptotically stable. Yeah. Okay.
There's a plus UD minus UD plus UD.
Which one? This one? Yeah, that's a typo, sorry. Yeah, so this is UP is equal to minus the gradient, and then the plus UD, this is just so this should be a plus, and this is correctly plus. Okay, thanks a lot. Yes.
In this you discussed that gradient is a covector.
Yes. The D, okay, good question. So the D of psi, the differential of psi, is the covector. And we can write it as, you can always take a row vector and write it as a column vector. This is what you know as the gradient. So whenever you say a gradient, okay, you usually mean, and you write the partial f by partial f by partial x1, and then below it partial f by partial x2, and you write it as a column vector, you're actually thinking of the vector version of the covector. In this case, they are simply take the row vector and write it as a column vector. But again, depending on the geometry that you have, they can be completely different. Today, we're going to be seeing an example of that. Okay, so this is the actual covector, that when you pair it with the vector, you get a number. And I can write the covector as the covector as a row vector, and then I have sorry, I can write the covector as a column vector. So I'm going to get column vector and column vector, right? How do I take two column vectors and get a real number? So x transpose y, right? So this is similar, x transpose y. So this is a column vector, this is a column vector transpose. But you see here, this, if I write it as a row vector, I just multiply it directly by the psi dot. Yes. It's only in R3, exact. What I write here is general. So the v dot is always the covector version of the sorry, there's something here that's missing. Yeah, okay. So v, I can write it, it's psi plus h. Okay. So the v dot, I can write it as the psi dot plus the h dot. And so this is the psi dot and this is the h dot, because each one is a function of the two separate variables. So I have a separation of variables here. So this one, so the rate of change of any variable that's a function of, here in the case psi, is equivalent to the pairing between this covector and the psi dot, so the variable dot. Okay. Any question? Yeah.
For QB and PB, they are matrices. This is because for x direction, y direction, z directions work.
If you think of, okay, here, if you go back, even to the standard proportional PD controller, it's sufficient to, you can choose KP to be positive definite, which means that they're going to have some stuff on the diagonal. So this is it will relate how the X error changes with itself. But you can also have the off diagonal terms. So this means that when I have an Y error, I'm going to get something in the X actuator. The coupling terms, exactly. So how can I have coupling terms? Yes, provided that you can show that the eigenvalues are positive. Okay, so we need in the end the Kp and the Kd to be positive, definite. So this is the tuning part. You tune it for different performance, right? If you have, for example, the pendulum, do you want it to stabilize like this, or do you want to stabilize like, or do you want to stabilize again, different performances based on the Kp and the Kd. You play around with these values. Any more questions? Okay. Yeah.
Complex globally, so less than so a positive definite. So choosing the values of these parameters in this matrix, it depends on the specification of the system.
On how the rising time and the settling time, all of this stuff doesn't exist in real life. Because go back to when you were introduced to rising time and settling time and overshoot and all of these nice stuff, they're only valid when you have a linear system that's only second order. So you have to be linear, single input, single output system. In real life, we don't have these systems anymore. Maybe in small MATLAB code, but not in real life. Maybe. Okay, but after a lot of approximations, you can write a system like that. But in real life, we don't have that. We use them as a guiding, or so as a rule of thumb. So if you say that, for example, you have some overshoot, then you can play around with the D term in the same way, or in the same guidelines that you use the settling time and the overshoot and so on. But can you write that, for example, the gains here are equivalent to the settling time there? This is much more complicated because in this example it's easy because this is a linear system. You can do some transformations for this linear system and try to analyze that in certain directions you're going to have the stability by looking at some eigen decomposition. but in general not. So we just use this idea of the settling time and the overshoot just as a guideline. Okay. Exactly. So this is how you tune it. If you're happy, you're done. Any number you choose is stable. That's the thing. Any number you choose for the KP and the KD, you're going to have global asymptotic stability, provided that these numbers are constitute in the end a positive definite matrix. Okay. Now SO3. How easy will it be? Let's see. R dot. So we're thinking again. So we want to design a proportional derivative controller on SO3. We're going to be thinking just for illustration purposes of a satellite. Okay, but again, this is applicable to anything that will have SO3. Including SE3. So SE3 will be SO3 on one part, and then we're going to have a translation on the other part. So we're going to be using everything we say today, even if you're interested in designing a controller for SE3. We're not going to have the time, unfortunately, to dig into SE3, but let's see how maybe we can include it next time, or still thinking about it. So, but at least SO3 is the fundamental one you need to understand. R dot is equal to R omega tilde, and omega dot is equal to the momentum balance given by this equation. And again, we have some torque, some control torque that we want to design. And our goal here, first we write it in the state space form. We're going to be following the same lines as we did for the point mass. We're going to be choosing the configuration variable along with the momentum. So we're going to be having the x's R and J omega. And so we have something that lives on SO3 and something that lives on R3. To be precise, the momentum is a covector, right? So it should be on R3 star, but it doesn't matter if I write the momentum as a vector or covector. In the end, it's just the momentum. Okay, so in fact, I'm writing the momentum here as a vector, so as a column vector, but we mean it's a covector in nature, right? Because it changes coordinates differently. We don't see that in SO3. If you remember, we never saw that momentum and velocity, they change differently coordinates, except when we went to SE3. And SO3, we're always changing in the same coordinates. So something to look at, to go revise it. The equations of motion, we can write these equations you're familiar with in this way that is important for our analysis today. They are equivalent. So R dot is equal to some function beta that is dependent on R. So it's beta of R is the name of the function. And it will eat some omega, some vector omega, and it will spit out some R dot. It will spit out something, a vector that lives in the tangent space to R, okay, to SO3 at the point R. How is this defined? So beta of R, when it eats an omega, is simply R multiplied by omega as a skew-symmetric form, okay? So if I give you three numbers, omega, how can you calculate from them R dot? Okay, you skew-symmetrize it first, and then you multiply it from the left by R, then you get the R dot. This is exactly what this beta R is. And then the P dot, I'm going to rewrite, again, the J here is constant, so we're going to put it on the left-hand side. So P dot is J omega dot. And this term in the middle, I can rewrite it as the skew-symmetric form of P multiplied by omega, or the cross product of P multiplied by omega. This and the P here is the angular momentum. Okay? Just to keep the physics in mind. And then we have here the torque. This is the map that's multiplied to it. So this is x dot is equal to f of x plus g tau. Here we're going to be keeping tau. Again, tau and u, these tau are the control inputs that we want to design. Yes?
You assuming the minus in the top?
No. So you see, you're absolutely right. So again, another typo. Thanks a lot, Farouk. Maybe you can spend the weekend trying to correct all of these. So you have the minus here. This should be inside of the bracket. And then this should be a minus. This should be a plus. Yes. Yeah. Thanks a lot. Yeah. If someone is taking notes, can you please just send them to me, all of these typos in the end? So we aim to design. So what we want to do is the following. We want to design a geometric PD controller. So based on this energy balancing idea that we discussed for the point mass. So we want to have tau to be a proportional term and a derivative term. And then we want to design this controller. What is our objective? Such that this state, which is some desired orientation and some angular velocity that's zero. So we want to stabilize this system. We want to design the control law such that this state is an asymptotically stable equilibrium point of the closed loop system. What is the closed loop system? Just plug in the Tp plus Td in this equation. So we just have, this is our closed loop system. It's a little bit, is this the same as we did for the point mass? The same structure, exactly everything is the same so far, but because of the geometry, things are completely nasty here. What is the first, there are two things that are clear from the closed loop system. This one compared to that one. What do you see immediately? We don't have the what? Delta, this one. So we don't have this nonlinearity, yes. So this is already nonlinearity. What else? The torque. The torque, we already had it there as the force, right? So we had the force acting, it was the U. We had the U as a proportional term and U as a derivative term. So both are the same. So these are actually were common in both. But this term, we didn't have it, okay? And the one on the top, this map, this nonlinear map that's depending on R, that will map the angular velocity to the R dot, we didn't have that. There we just had that the psi dot is equal to the V. But here, because of the geometry, so R dot is not equal to V or omega directly. We just have this map. So this will complicate stuff, like you can imagine. Yes. They're the same. This is the same. Yes, of course. Yeah, we're going to be seeing later. Yeah. Okay. So we aim to have a geometric controller. What does a geometric controller mean? We want it to respect, okay, or satisfy any constraints that we have from the non-Euclidean structure of SO3. Okay, so SO3 is not a vector space. Okay? You know that for sure by now. And then, so we need to designing this tau P and tau D will not be an easy task. Okay, if we want to have this geometry being respected. So tau P, how will we derive it? We will be deriving from a gradient of some positive definite potential function on psi, capital psi R on SO3. We want to design this capital psi such that it has a minimum at R is equal to R desired. Okay. And tau D will be designed such that we inject damping and we make sure that we have a negative semi-definite Lyapunov function. What will be our choice for the Lyapunov function? It will be psi of R plus the original energy that the system had. This system is just a satellite moving around, so it only has what kind of energy? Just kinetic energy. How do you calculate this kinetic energy? Half omega transpose J omega. Or in written in terms of the momentum, it's 1/2 P transpose J inverse P. Right? They're exactly the same. So you see the analogy between the point mass and the satellite. They're very much, there are a lot of stuff that are similar because both are mechanical systems without any damping, and we want to design a proportional derivative controller for both. But the geometry of one is R3 and the geometry of the other is SO3. So this is the only thing that's different. So these are we need to solve these 5 questions. If we can do that, then we have a proportional and derivative controller in SO3. The first one is that, what is the error? If I have a actual orientation and a desired orientation, okay, can I just say R minus R desired? No. So how can we design the error? That's the first thing. So just a measure between the difference between both. Then if I know this error, how can I design this potential function of the error to be positive definite? And this is, of course, the choice that I can have. This is just a choice. You choose the psi, and then everything follows from there, just because of the geometry. But if you change the psi, you get a different controller. All of them are PD controllers. All of them are geometric. They just have different performance, different ways of how it will stabilize the system. Even if we have a psi in mind, how can we compute its differential, which is the covector version? And of course, the covector lives where? Lives in the cotangent space to SO3 at the point R. It's no longer R3. How do we convert, but the torque we have are 3 numbers. We have 3 torques that we want to apply to the satellite. How do we convert this covector? You don't know what structure, what does it look like? How do we convert it to a proportional torque? And then after we have the proportional torque, how can we design the derivative torque tau D? Okay. Which one do you think is the easiest? The first one. Okay. Maybe we can come to the board and do it. Okay, let's do it. Yes. Yeah.
the cold tangent space, is it not dual to R3 star?
That yes, it is. Not dual, it's isomorphic to R3 star. Yes, that's right. And this is precisely what we're going to be using to derive this controller. Yes, absolutely. Any more questions here before we start? Okay, this lecture is very technical. Very, very technical. So we're going to be writing a lot, so keep up, okay? Try to write and try to keep up with all of the writing. Okay. So the first question is, what is the error between R and RD while both live in SO3? Okay. The picture that you should have in mind is that we usually, whenever we have a mechanical system in mind, in this case, this satellite, we already have an underlying stationary frame that we chose, right? This is our home orientation. And then we have the body fixed frame B, which is, in this case, it's the same origin, right? So they are both on the same place. They're just rotating without any, okay, any translation between both. I'm just drawing it like this so that you can see it visually, okay? We also have another desired frame. And again, all of them, they are coincident at the same point. They're just rotating with respect to each other. When we're saying R, we're implicitly meaning which one of these? Which relative orientation? When we say R, the R of the satellite? There's no such thing as RB. There is always RB with respect to S. So whenever we say R, we're actually meaning the relative orientation between B, the frame B, and the frame S. Okay. And when we say RD, which one do we mean? D with respect to S, exactly. These three dashes, they're this equivalent sign. It means that R and RBS are two notations for the same thing. Okay, this is not an extra information. There's just two notations for exactly the same thing. Okay? So whenever we say R and RD, you should have these two rotation matrices in mind, or these two relative orientations. The error that you have in mind, so, is nothing else than the relative orientation between the frame D and the frame B. And you can write it as B with respect to D or D with respect to B. We're going to be writing it as B with respect to D. Yeah. So, what do we get? Can write it as RS with respect to D multiplied by RB with respect to S, or in other words, RD with respect to S transpose, RB with respect to S. Right? So the error function that we're interested in, again, if we introduce another notation for this error function, let's call it RE. So if we just say RE, again, here we're going to remove all of the indices just to make it easy to track because we're going to have, again, a lot of equations. So we're just going to be defining RE to be RD transpose. Okay. RD transpose multiplied by R. What is the value that we wish? So our goal, you have a question? So we don't have an end effector here because we're not talking about a robotic R. But if you're talking about a satellite, so the body fixed frame, we just have one rigid body. So we do want to have that this orientation of the satellite, or the relative orientation between B and S, to be the same as D with respect to S. All of them are at the same point. So then B with respect to S will be as D with respect to S, and both of them will coincide with each other. This is our desired goal, that we want B to coincide with D. We want frame B to coincide with frame D. So So let's say that the satellite looks like this. I want it to transform, I want it to rotate like this. Okay, so this is the D and this is the B, right? And I want both to coincide to each other. I take the transpose of one multiplied by the other, transpose of the desired multiplied by the actual one, or the one of the satellite, or B with respect to S, then I define the error.
There is difference between taking B related to D and D related to B.
The control law will look differently, and you should expect that you're going to have just one rotation in the end. They're equivalent, but you just have one as the rotation of the other. Because they're just, again, they're just in the same torque expressed into different frames.
Eventually, in the final eventual action of the torque, will it be different?
The torque will be the same, but if you write one as in terms of R, B with respect to D, and I want to rewrite it as something with D with respect to R or B, this stuff will just change. And also the meaning of the gains will change. This is also another thing. Okay, we're going to be doing it this way. There was a question, yeah.
Just R of D with respect to B.
D with respect to B. So the opposite. That's exactly Farouk's question. You can do that. You're just going to get another controller. Both of them are exactly the same. They just look differently. Okay. Any questions? Okay. So now our goal is that RE would tend to identity as T tends to infinity. If we can show that RE tends to identity, what does it mean that RE tends to identity? Then RD tends to R tends to RD. Okay, so then we have this stabilization. So this is the first point. So this is you're true. This is the easiest thing so far. Okay, so this is the easiest thing of today. The next question is, how do we define the potential function, or what potential function can we choose? So just as a side point, remember that when we discussed the case of R3, we said that our potential function as a function of the error, okay, between psi and psi desired was a quadratic function. It looks like this: P psi transpose Kp E psi, right? And this is written as a function of the error. And when we used it in the Lyapunov analysis, we wrote it as a function of, so this is also equivalent to being a function, of psi. And then we wrote it like this. We wrote it half psi minus psi desired transpose Kp psi minus psi desired, right? Everyone agrees? Okay, just as a reminder of what we did last time. Now let's look at the potential function we're going to be writing as a function of Re. We want something that will have a minimum when R is identity. Okay. The function that I'm going to say what it is, derive everything for it, and then if we have some time in the end, I can tell you how you can actually come up with it. Okay, so how to do it the other way around. But it's much more easier to follow the line of thought, and because you're seeing this for the first time, just to have it given like that. Okay, so I'm not going to motivate where does it come from, but you're going to see, okay, throughout when it's derived, actually this is doing exactly what we want. So this potential function is half the trace of the identity minus Re. Yeah. And I can rewrite it differently. So here, this is written as a function of the error. If I also write it as, so this is, or I can write it as a function of R, then it will be written as half the trace of identity minus R desired transpose multiplied by R. Just clean up this stuff. So let's see if again, just from a matrix point of view, does the dimensions work? So this is a 3 by 3 matrix, 3 by 3 matrix. The transpose of them, so the transpose of one multiplied by the other is a 3 by 3 matrix. This is a 3 by 3 identity matrix. Can you take the minus here? Can you take the minus? Yeah, that's okay. Okay. So I can take the minus of these two. What do I get? I get a 3 by 3 matrix. Okay. Then I take the trace of that. What do I get? Just one number. That's it. So we just have now a function. So now we have a function that goes from SO3 to a real number. That's it. If you're a little bit annoyed of the fact that we do the minus here, okay, this is only to convert it to a real number, but this part is still on SO3. So this part by itself is still on SO3. And we have a function that goes from SO3 to R. Okay.
Our goal is to make it minimum at RE equal identity, right?
Maybe we already have that. So let's see actually if we can check for, okay, so we have these two functions. In some cases, I'm going to be using the first one, and some other cases, I'm going to be using the second one, depending on whether we want it written in the error or in terms of R, okay? Just like what we did in these two there, okay? So here I'm going to use the first one. So if I have the SAR of R of identity, or let me write it explicitly, that RE is identity. What do we get? We get that it's half the trace. You guys know how the trace is calculated? It's just the sum of the diagonal, exactly. So we don't look at the off diagonal terms. We just take the sum of the first one on the diagonal plus the sum of the so first one on the diagonal plus the second one on the diagonal plus the third one on the diagonal. We're talking about SO3 here, so we only have 3 by 3 matrices. So this is half of trace I minus I. What is it? 0. The question is, when we go away from it, do we have a positive number or not? So we need to show positive definiteness. So psi of RE, we can rewrite it in a very, very nice way. That will so this is a very short proof, but with all of the tools that you already know. So there's nothing fancy there. We can write it as, so this equation over there, which is half of trace I minus RE. First of all, the trace is a linear operator, okay? So if I have the trace of A plus B, it's equivalent to the trace of A plus the trace of B. So I can rewrite this as half of trace I minus half of trace RE. Okay? What is the trace of the identity matrix? What's the trace of the identity? Just the trace of the identity matrix. 3, right? 1 plus 1 plus 1. So this is equal to 3. What is the trace of the rotation matrix? No matter what the rotation matrix is. Can we have like a closed form solution to show that this trace, whatever the rotation matrix is, we're going to get something that maybe it's bounded, okay, so that we can look at the psi of R? The highest is 3. That's correct. The highest is 3 if you have this to be an identity. But if it's not identity, can we show very nicely that it is bounded? Now let's show this very as a proof, as a like a small lemma. But first, we can rewrite this term as 1 minus cosine theta for some theta. Okay, that's just the rotation, the angle version of this rotation matrix. Now, so this is just take it as a result, and the proof of it is here. So remember that we can use Rodriguez formula to write any rotation matrix as the sine of some angle and some axis. So we can always write a rotation matrix by locally as the angle and an axis, right? So this is just a parameterization of the rotation matrix. So this is a unit vector, and this is the angle. So we have these 3 numbers in the end that, so these 3 degrees of freedom that correspond to the rotation matrix. And the Rodriguez formula, if you remember it, was given by this expression. So I had identity plus sine of theta multiplied by the skew-symmetric version of this unit vector plus 1 minus cosine theta multiplied by the skew-symmetric matrix square. The trace of any, so let's take the trace of RE. You can show that this is equal, the trace of identity is 3. The trace of, again, the trace is the linear operator, which means if I have the trace of some scalar multiplied by a matrix, what do I get? I get the scalar outside because it's a linear operator or a linear map. And then I have the trace of the identity, sorry, the trace of the 3 by 3 matrix. So this is the same here. So the trace of the sine multiplied by the 3 by 3 matrix is equivalent to the sine multiplied by the trace of the skew-symmetric matrix. The trace of the skew-symmetric matrix is equal to 0. Then I have the same here. So I have 1 minus cosine theta multiplied by the trace of this term. You can show, okay, it's very easy to prove it for yourself, that the trace of the skew symmetric of a skew symmetric matrix, any skew symmetric matrix multiplied by itself, so squared, will be equal to -2. So this is 1 minus cosine theta multiplied by -2. Okay, you can show it for yourself. It's very easy. So in the end, we have that the trace of RE can be written as 1 plus 2 cosine theta. And if we plug in this expression, so trace of R, into this formula, you can show that the psi of RE is in the end simply 1/2 of 3 minus 1 minus 2 cosine theta, which is equal to 1 minus cosine theta, and then we have a proof. Yeah. Okay. This is just quick math, but again, if you follow it at your own pace, you're going to find, inshallah, everything is true. Yes.
Where does the theta come from?
I'm saying that I can write the R as any, okay, I can always find this to be any theta and any, so any vector n hat, right? If we go back to when we look at the exponential map, we can always write a rotation matrix by some theta. I'm not saying what the theta is. I'm not saying how to calculate it. I'm just saying there is some theta that you can write any R as into it. You can transform it into it. Okay? Yes.
So coming back to our arrow here.
It's a potential function of the error. Yes. Just like the quadratic function of the error. Yes.
So when we're discussing initially the situation of each being SO3 and the structure of the manifold itself, you mentioned that we could take the difference of the identity and this element of SO3.
Yes.
But isn't that violating?
Is this a map from SO3 to R? Yes or no? That's it. We have what we want. We're not violating anything. Okay. I see your point. That it's this minus, right? But I'm not saying that this is an SO3. I don't want this to be SO3. I just want this to be SO3. That's okay. SO3 is still a 3x3 matrix. So I can still have something minus this. If you want to come up with something better and not to have this minus, this is part of the research, right? And I think there's some stuff in the literature that try to not to have this minus there, trying to, again, try to have some sort of exponential maps and so on. But again, what we're saying here is this is one possible choice of the potential function. This is a map from SO3 to R, so it's 0 at here. And if we just take this result that we had, you can actually show that when we have the identity, then we have this to be equal to 0, cosine of, so that when we have R is equal to identity, then theta is equal to 0. Okay? If you take the axis angle representation of the identity matrix, you just get that the theta is equal to 0. You're not doing any rotation. Makes sense. So the cosine of 0 is equal to 1. So 1 minus 1, we get 0. So this is what we already know. But what about when we have any value, okay, for theta? We know that the cosine is between what and what? Between pi and minus pi. So in the end, between what and what? Between 1 and minus 1. So in the lowest case, when we have this to be minus 1, what do we get? We get the maximum, which is 2. When this is 1, we get 0. So in the end, we actually have a proof that this function psi of RE is between 0 and 2. And it's only 0 when we have that theta is equal to 0. And theta is equal to 0 only when RE is equal to identity. And RE is equal to identity means that R is equal to R and RD are the same frame. Okay, so they are the same thing. Any question? Yeah.
So just coming back to the statement, because I'm trying to link it to the conversation. about the potential function itself and the error function. So what makes this permitted or permissible is that for the error function, it would have violated the
Yes,
and we wanted it to be equal to another element of X.
exactly. Exactly. Yes, absolutely. So this is our function. So we have a positive definite function that has a minimum at our desired point, and it satisfies. Okay, so it's a valuable positive Lyapunov function if we want to do any Lyapunov analysis. Okay. Now the question is, so the third point is, how do we compute the differential? So the differential of psi of r, how do we compute it? But to understand really how this works out for psi, and again, here psi is a function that goes from SO3 to R. Let me ask you another question, which might seem very silly. How do you define the differential of a function that lives on a vector space, R3, for example? So I give you any function, and I tell you take the differential of it or the vector version of it, which is the gradient. You know how to do it, right? How is it defined? You know how to do the differentiation, but how is the gradient defined in the first place? Okay, this is something maybe you took it in the first week or in the first day you were introduced to the gradient in a very old math course that you completely forgot about, maybe most likely didn't understand it at the time. We need to revisit this definition of actually how is the gradient defined, or equivalently, how is the differential defined? So we're going to be doing on two cases. Let's look at functions on a vector space and functions on a manifold and see how to define it. Question?
Going back to first principles.
Going back? Of course, yeah, of course. We need to go back way back. Okay, yes. So let's look at the differential of a function. So this is the differential of a function on a vector space. And the vector space here is not necessarily Rn, but it could be Rn. Okay? So Rn will be will be a special case of this. So let psi to be a function from the vector space W to R, and it's defined such that it will take any point X, because here we have a vector, so this is a vector. So we have a vector space, so X is a vector in W, and it will take us to a real number, psi of X. And W is any vector space. So the differential of the function psi is the unique covector d psi of X. Where does it live? W star. If we're thinking of a vector space that's W, then the co-differential lives in W star. That satisfies the following. When I take the d of psi of X, what is the nature of this object? It's a covector, which means I can pair it with what? With vector. Any vector or a particular vector? Any vector. It can eat any vector and it will spit out a number, right? So I can pair it with any vector. The standard notation of this vector that's just any vector is delta X. So delta X is not a small thing. It's just any vector that's in the vector space. Okay, we can write it in any other notation, but you're going to find this standard notation in, I would say, a lot of math textbooks. So, and this pairing is the pairing of the vector space. So we need to look at the vector space, and so that we can take the pairing between this covector and the vector. If you have this left-hand side and you can show that this is equivalent to, when you plug in here this covector, it is the covector that we're interested in, the differential of the function, is the covector that when you plug it in here, it will satisfy this expression. And this is valid for all delta X in the vector space. I'm 100% sure you've seen this in one context or the other before. Just take a moment at it to try to remember if you've seen something like this before, and please raise your hand if you did. Maybe not in this generality, but at least this right-hand side, that the d of the differentiation with respect to some small epsilon, okay? Or the limit, you can maybe you have seen it in terms of the limit, right? The limit as this goes, as epsilon goes to 0, that when you take x plus a small epsilon multiplied by this vector, you get this equation. Who's seen something like this before? Or does it ring a bell? Or maybe 1, 2, 3, 4. That's good enough, okay? It's not 0, okay? It's positive definite. So with this definition, okay, you can derive the gradient, or in this case, the differential of any function. And this is precisely what you do immediately blindly while doing the partial derivatives. Okay? Let me show you that this will recap something that you already know how to do. Let's look at the case. Just look at an example of psi and Rn. So let's take the example for psi, capital psi of small psi is equal to half. Okay. Maybe, okay, let me remove this to be a x, just to make it simpler. Let's call this x. So this is half x transpose kx. If I ask you what is the gradient of this, what do you do it? So it's a no-brainer, right? It's kx. And kx is the vector version. If I write it as a covector, it's x transpose k, right? It's just the transpose of it. Can we just use the definition we just said and try to show the same? So let's compute d psi of x. This is the case Rn. So where does this covector live? It's an Rn star. So let's calculate, if you go back, let's calculate the right-hand side first, okay? So psi of x plus small epsilon multiplied by delta x is equal to half psi, x, and then we have the delta x transpose x plus epsilon delta x, which I can rewrite as, I can expand this, okay, as half x transpose kx plus epsilon delta x transpose kp x plus epsilon squared over 2 transpose kp. Okay, they're all quadratic terms. Okay, maybe let me try to reorganize it. Okay, so half x plus y transpose multiplied by kp. So x transpose multiplied by x transpose kx, x transpose ky, y transpose kx, y transpose ky. Okay, and here we assume that the kp is positive. Oh, sorry, the k here should be, I wrote it here kp, so this is kp, and the kp is positive definite, which means, and it's symmetric. Okay. Now let's so this is this equation. Let's take the differentiation with respect to epsilon, and after we take the differentiation, substitute with the epsilon is equal to 0. What do you get? First of all, this term. So we have 3 terms. This one is not a function of epsilon, and this one is only a function of epsilon, and this one, there's actually something missing here. It should be epsilon squared. It's quadratic in epsilon. when is this a function of what happens when you differentiate this with respect to epsilon? Okay, what happens when you differentiate this with respect to epsilon? You get the same term without the epsilon. What happens when you differentiate this with respect to the epsilon and then substitute the epsilon to be 0? So in the end, this is equal to delta x transpose kp x. Or, because it's a symmetric term, I can rewrite, sorry, it's a scalar, so I can rewrite it, sorry. This is the differentiation with respect to epsilon of this expression. And this is equivalent to, I can rewrite it also as this guy, or kpx transpose delta x. Okay? So far, so good? I only did differentiation with respect to one variable, epsilon. Then let's look at the differential of psi with respect to x. And then we said that if we pair this with any delta x, okay, and we're living in Rn, how is this pairing defined on Rn? We need to know how this is defined on Rn, otherwise we cannot continue. How is, if I give you a covector and a vector on Rn, how do you pair them to get one number? If we say this is a covector, then we wanted to write it as a row vector, and then we just multiply it by the vector. So this is just multiplication. There is here a dot, and this dot is that you're multiplying a row vector with a column vector, okay? Now let's compare this part. Again, we said that this covector is the one that satisfies that this term, which is the left-hand side, again, go back to this expression. The left-hand side of this expression is equal to the right-hand side of this expression. So we calculated here the right-hand side to be equal to this, and the left-hand side to be equal to that. So what can you conclude about this term? So if we compare, so by comparing, or by comparison of right-hand side RHS and left-hand side LHS, therefore we conclude that d of psi of x is equal to if I transpose it to write it as a gradient, what do I get? kpx. So this is a no-brainer if you want to calculate in a very systematic way the gradient without knowing even about differentiation of multivariable functions. You just follow this. You only do differentiation with respect to one variable. And this is the definition of how you do the multivariable differentiation or the gradient. This is the definition of how you do the gradient. So the fact that you're very good at saying, okay, the gradient of this is just, I have the 2 multiplied by kpx. You've already done all of this in your mind, again, implicitly, to reach this conclusion. Make sense? We need to have this definition so that we can extend it, okay, to the case of a manifold. So part C is how do we compute the differential of a function on a manifold? We're not going to, we don't need this function to be, we don't need this manifold to be a Lie group. We're going to be defining it as a manifold, and this will hold for the case of SO3, okay? Because again, a Lie group is a manifold and a group, okay? So both are a group, they both are a manifold, yes.
It seems like in the definition itself, we are differentiating.
No differentiation at all. Go back here. The right-hand side. The right-hand side is differentiating with respect to epsilon. Yep. And the left-hand side is just the name of the covector. All of this is a name. You can call it capital gamma, call it whatever you want. Okay?
So in order to get the differential with respect to particular variable x, then we differentiate with respect to epsilon.
Yeah, exactly. We take this like a perturbation, the whole idea is that perturb a little bit the x that you have and see how it varies, and then this is the gradient. This is exactly what the gradient does. Okay, and you already maybe know that, okay, the gradient of a function, a multivariable function, will tell us how the function will change in the next point, to the right or to the left, right? So this is exactly the same, but in a multivariable sense. So the third point is that how do you compute the differential of a function on a manifold. So let psi to be something that goes from M to R. So the manifold we're interested in is M, and such that it will eta x and spit out a real number psi of x. So the differential of psi is the covector. Again, is the unique covector d psi of x. Where does it live?
Dual space.
Dual space of what?
Of the tangent
Tangent
space
space.
to SO3 at the point.
That's right. The cotangent space at the point x. You see here, this is a function of x. So we need to know where the x is. So we're locally at x, and this lives in the cotangent space to the manifold. That satisfies that the d psi of x paired over the tangent space to the manifold at the point x. So where is this delta x living? So that satisfies for all delta x that lives in this tangent space. D by d epsilon, epsilon is equal to 0, psi of, if I put here, let's go back to the standard definition of the vector space, right? So this is the same as the left-hand side. We just have a different vector space here. But the right-hand side, if we go back, we're going to find that we need to have, in the vector space case, we say x, which is the vector that I had, plus some epsilon with the vector. Can I have this on a vector space? I do have the plus, right? I have the plus operation. I take two vectors. Okay, so this is a vector, this is a scalar. What is the result? A vector. I can take the sum of two vectors. What do I get? A vector. I can take the function of a vector. So everything is valid geometrically. If I write here the same, will it be possible? No. A manifold does not have a vector space structure. So I cannot say x plus something in the vector space. So we're going to be introducing something called x sub e, or x sub epsilon. And what is this x sub epsilon? I'm just gonna draw the picture here. So the picture that we have is that we have a manifold, and we have a curve x e that, that when epsilon is equal to 0, so epsilon here is the parameter of the curve, okay? And x is the point I start with. So epsilon equal to 0 will give me what? Will give me the point that I'm interested in, the x. Okay, so I'm trying to vary starting from this point x. While the vector, which is this delta x vector, is the tangent. Let me choose another color. Is the tangent vector to this curve at the point x. So delta x here lives in Tx m. Okay. So this is the definition. So such that, so where x. So this is just the picture, and I'm just going to write what I just said. So where x epsilon is a curve on M that's defined as, when I have this vector, sorry, when I have this curve and I evaluate at x at epsilon equal to 0, what do I get? I get the point x on M. While when I take the d by d epsilon and evaluate at epsilon equal to 0 of this curve, and this is the definition of the tangent vector, we get delta x, which lives in the tangent space like this. This is the definition of the covector. It's very abstract, doesn't make any sense. Okay? We need to apply it. So we're going to be doing it now for the manifold that we're interested in, which is SO3. And this is the last part of today's lecture. So the example,
Something that is not there in the previous thing.
where?
SCE is a common M. It's like parameterization of the manifold.
Yeah. It's a curve, okay? That this is the name of the curve. Okay, here I'm doing just an abusive notation where I'm calling the curve and also the point where it goes by the same symbol. Okay, this is just an abusive notation. Okay.
In derivative here, we're only differentiating at the beginning, not at all the points along the curve.
The differentiation is always like that. You take the time derivative and then you evaluate the point we're interested in, right? Just like with the gradient, right? With the Jacobian, you take the partial derivatives and then you substitute the point. It's exactly the same. So we take the derivative of the curve and then we substitute at epsilon equal to 0. So the example is R lives in SO3. So this is the manifold we're interested in. What is the function we want to discuss? It's this function, trace of I minus RD transpose R. So this is the function we're interested in finding the differential of. So how do we compute d psi of R? Where does this live? In the cotangent space to SO3 at the point R. So if we go back to the definition, we have a right-hand side and the left-hand side. The right-hand side is equivalent to this RE, the R epsilon, and it's half transpose I minus RD. Half the trace, sorry, not the transpose, half the trace of I minus RD transpose R epsilon. Okay. I'm changing a lot between this notation. Sorry. So this is let me write this as blue, so that it's always clear what we're talking about. So this is R epsilon, and this is R epsilon. So the d of d epsilon with respect to epsilon, and then evaluating epsilon equal to 0. Just like let's differentiate this function. You just need to know a couple of properties, and then it's straightforward to do it. The first one is that the trace is a linear operator. Okay, so doing the differential of it, okay, is equivalent to taking the trace of the differential of what's inside. So if I take the d with respect to epsilon of this function, it's equivalent as having half the trace. First of all, let's rewrite actually this. Maybe it's easier. Let's rewrite this as half the trace of I minus half the trace of RD transpose RE, or epsilon. So writing it like this, and again, we want to take the differentiation of respect to epsilon at epsilon equal to 0. This term here is what? Is 0, because it's not a function of epsilon, so when you differentiate it, it will just pop out. So in the end, I only have this second term. So I want to have, so this is equivalent to minus half the trace of the d by d epsilon, when epsilon is equal to 0 multiplied by RD R epsilon. So what happened here is that this differentiation of the trace of a matrix is equivalent to the trace of the differentiation of the matrix. This is just the first property we're using. The second one is that this is the matrix multiplied by a function of epsilon, and this is a constant that doesn't depend on epsilon. So I can rewrite this as the differentiation of, so instead of having the differentiation of these two terms together, again, we can have when we have the differentiation of A multiplied by B, it's equivalent to differentiation of A multiplied by B plus the differentiation of, plus A multiplied by the differentiation of B. The differentiation of the first matrix with respect to epsilon will give you 0, because it's not depending on epsilon. So in the end, I'm going to have the following. I'm going to have, this is minus half, sorry, okay, okay, let's keep it. There's just a minus sign that's annoying here. Okay, let's just keep it. So this is half trace of R D transpose D by D epsilon. Epsilon is equal to 0 of R. So, okay. Can we change this to be something? So when we differentiate this curve, what did we get? To go back, you see here, when we differentiate the curve, we get this vector, right? We get this vector that's in the tangent space that we call it delta. In this case, we're going to call it delta R. So this is equal to minus of the trace of RD transpose multiplied by delta R, which is the vector we're interested in. Now, this is the right-hand side. Now, let's look at the left-hand side. If you go back, the left-hand side was the differential paired with the delta R that we just talked about, that we just introduced. But we need to look at the pairing on SO3. So how can we define that? So the differential of psi with respect to R paired with the delta R on TR or SO3 is equivalent to, okay, what is that? So this is, so when we have R dot that lives in a tangent space, what was the size of it? What's the dimension of it? R dot. 3 by 3 matrix. The covector version of it will be also another 3 by 3 matrix. If I give you two 3 by 3 matrices, can you convert them to a number? Multiply them together, you get a 3 by 3 matrix. Do you can think of any way that transform this to a number? The trace. Exactly. So the pairing on SO3, or the pairing on the tangent spaces of SO3 is nothing else than this guy multiplied by that guy. Okay. Just like when we had a covector multiplied by a vector in three, and like a 1 by 3 vector multiplied by a 3 by 1 vector, we give a number. Here we have a 3 by 3 and a 3 by 3. We get another 3 by 3 matrix, and the trace will make sure that we have this in the end number transformed into a number. Now compare this to the left, to the right-hand side. You can show in the end straightforward that the differential of psi at the point R is nothing else than minus half RD transpose. To be continued. Okay, inshallah. Any questions? Okay, let me stop, okay, because the time's up and you can have the questions offline. Okay, jazakumullah khair.